Welcome back to the deep dive. Today, we are wrestling with a technical domain that is just absolutely packed with what you might call information density, the service mesh.
Right.
If you're building modern applications with microservices, this is that invisible infrastructure layer that's managing every single call, every policy, every security handshake.
It's the ultimate complexity extraction layer.
Right.
I mean, you delegate all the hard stuff like security, routing, resilience to the mesh.
Right.
But that means you, the administrator, you need a flawless mental model of how to actually configure it.
Exactly.
Knowing which resource controls which lever is.
Yeah.
The difference between a successful deployment and a full-scale outage.
Exactly. And our goal today is to give you that mental model. We've taken some source material. It's derived from preparation for these hands-on performance-based exams like EX328. And we're using those high-value points not as a test, but as a deeply structured guide.
So our mission here is to extract the 10 most critical service mesh concepts and resources. If you walk away understanding these 10 points, how they pair up, why they're separate, you will have the essential vocabulary for any advanced microservices operation.
So let's unpack this. Let's start with, I think, the most fundamental challenge in any distributed system.
Okay.
Just getting the traffic where it needs to go, reliably and, intelligently.
Routing, job number one.
Imagine you just deployed a new version of your user auth service, V2. You want to test it, but you can't send all your users to it yet.
Right, a canary deployment.
You need to do a canary deployment. Send 10% of traffic to V2, keep 90% on the stable V1.
Which core resource is the decision maker here, the one that handles that weighted traffic split?
That is the sole responsibility of the virtual service. We call it the router's brain for a reason.
The router's brain!
It dictates how incoming requests, based on the service name they're trying to reach, are mapped to actual workloads. If you need timeouts, retries, traffic splits, it all goes in the virtual service. Okay, but what if we want to go beyond just a simple percentage split? Our sources highlight this ability to do really sophisticated conditional routing. What if I want to send that 10% to V2, but only if the request came from our internal dev network, which I can identify by a specific HTTP header?
Ah, that's the power of the match field.
Match.
To define that precise condition, say routing to V2, only if the header user type equals internal, you use the match field right inside your virtual service config.
So it's like an if-then statement.
It's an evaluation engine. You're telling the mesh, evaluate the request, and if it matches this condition, then apply this specific routing rule.
So virtual service is the ultimate decision maker, the route, but it's almost always paired with another resource.
The destination rule.
And this is where I think a lot of new learners get confused. If the virtual service is deciding the route, why do we need a destination rule?
That is the critical architectural separation. Think of it this way. The virtual service is the train conductor. It decides which route the train will take.
The dynamic decision.
Okay. Exactly. The destination rule is the rule book for the tracks themselves. It handles the static policy and definitions after that routing decision has been made.
So what are the main things the destination rule defines then?
First, and most critically, it defines the subsets of your service.
Subsets?
Yes. If you have 5 versions running alpha, beta, V1, V2, you need a destination rule to define those groups based on their Kubernetes labels. The virtual service can't route 80% to V1 unless the destination rule has defined what V1 actually is.
Ah, okay.
And second, it defines policies that apply to those subsets, things like specific load balancing algorithms or connection pool settings.
So the virtual service says, send 10% of traffic to the V2 subset.
Right.
And the destination rule says, by the way, the V2 subset is any pod with these labels, and when traffic gets there, use round-robin load balancing.
You got it. It separates the highly dynamic routing logic from the stable operational policies. It makes perfect sense for scalability.
Okay, that covers internal traffic. Let's shift focus now to, architectural necessities. Managing the edges of the mesh and optimizing the little workers inside.
Right, efficiency and boundaries.
The sources point to a massive performance bottleneck in large default deployments. The sidecar proxies, those little Envoy proxies next to every service, they synchronize info about every single service in the whole mesh.
Yes.
Regardless of whether they even talk to them. That sounds like a gigantic waste of memory.
It is. It's the architectural equivalent of getting 10,000 corporate emails when you only need to read 2. In a large mesh with hundreds of services, that configuration burden becomes huge. And that is why the sidecar resource exists.
So its core function is what exactly?
Performance optimization
Technically.
through scoping control.
Scoping control.
By defining a sidecar resource, you restrict the set of services that a specific Envoy proxy is allowed to see and talk to. You're basically creating egress rules.
Right.
You tell the proxy, you only need to know about these 3 services. Ignore the other 997.
So you're trimming the configuration fat for a healthier proxy.
Dramatically. It reduces config size, speeds up initialization. It's a huge win.
Okay, that's internal efficiency. But if we're talking boundaries, we have to talk about the front door, the part of the mesh that faces the outside world.
That would be the Ingress Gateway resource. The gateway defines the boundary listeners, the ports, the protocols that let external traffic into your managed environment. It's where the outside world shakes hands with your secure internal mesh.
And that handshake needs to be secure. So if I'm terminating HTTPS at the gateway, I need to give it my TLS certificate and my private key.
Of course.
How does the gateway configuration know where to find those credentials?
You specify the location using the credential name field inside the gateway resource itself.
Credential name.
Yep. That field points directly to the name of the Kubernetes secret that holds the TLS cert and the key. It's the secure link between that external connection and the crypto material it needs.
Okay, so we've got traffic flowing, proxies are efficient, the entry point is secure, but, no system is perfect. Let's talk resilience. What happens when things inevitably go wrong?
Right. We need robust mechanisms to prevent a single unhealthy service from causing a cascade failure.
The circuit breaker.
The circuit breaker approach.
Huh.
And in the mesh, the mechanism is called outlier detection.
Okay, we all get the basic circuit breaker analogy. But how does outlier detection actually work here? What does it consider an outlier?
It's way more sophisticated than a basic liveness or readiness probe. Those just check if the service is up. Outlier detection is monitoring runtime behavior. It's looking for abnormal error rates or latency.
So it's watching for patterns.
Exactly. You might configure it to say if a specific host returns 5 consecutive 5MyX errors, it is now an outlier.
And once it identifies that host as an outlier, what's the crucial action it takes?
It temporarily ejects that host from the load balancing pool. It just stops sending traffic to that unhealthy instance for a configured amount of time. This gives the host time to recover or be replaced, all without hurting the overall service.
That's incredible automation. But resilience is only as good as our ability to test it. I shouldn't have to wait for a real failure to see if my circuit breaker actually works.
Precisely. You need to use fault injection to simulate failure safely and intentionally. This lets you validate your app's failure tolerance without, actually disrupting production.
Or only disrupting a small, isolated part of it.
Exactly.
Now, there are a couple ways to inject faults. If I want to simulate slowness, I'd use a delay. But what if I want to simulate an outright failure? A host is down, a database timed out. How do I generate a hard error, like a 503 service unavailable?
For simulating hard errors like a 503, you use the abort fault injection mechanism. Abort is designed to just immediately terminate the request and return a configured HTTP error. It's how you can confidently verify that your upstream services handle that sudden, absolute failure gracefully. You can check their retry logic, their fallbacks.
Excellent. So we've covered traffic, performance, resilience. Let's move to the bedrock of modern service mesh functionality: security. Specifically, securing that service-to-service communication, east-west traffic.
This is where the mesh really shines. It moves security out of the application kite and into the infrastructure layer. You want cryptographically verified mutual authentication between all your services.
That sounds like mutual TLS or MTLS.
Right.
Which resource lets us define and enforce MTLS across the mesh?
That is the Pure Authentication resource. Think of Pure Authentication as your global knob for all things MTLS. It controls the specific modes of operation.
And what are the key modes we need to know?
The 2 most important are strict and permissive. When you set it to strict, MTLS is absolutely required, no exceptions. If you set it to permissive, the service will accept both plain text and MTLS traffic.
Which is really useful for like a gradual rollout.
Exactly. You can introduce MTLS gradually without breaking everything at once.
And the power here isn't just that it sets the mode, but where it can set it. It's super granular, right?
Absolutely. You can enforce a policy globally across the whole mesh, or you can scope it down to a specific Kubernetes namespace, or even apply a unique rule to a single workload. It's not a blunt instrument.
Speaking of global control, a service mesh is a huge piece of software itself. How do we manage the actual installation? The control plane, the brain that distributes all these policies, That must be configurable too.
It certainly is. That customization is handled by the top-level configuration object, often called the Service Mesh Control Plane resource.
So this isn't for my application, this is for the mesh itself.
Precisely. It's where you customize global mesh features. Integrating observability tools, setting default sidecar behavior, managing metrics collection, ensuring tracing is enabled. It's the central nervous system for the whole deployment.
Fantastic. Okay, we've configured the flow, secured the channels, customized the control plane. We're almost done, but there's one critical step left. Validation. How do we, the admins, actually verify that our 10% traffic split or our new security policy is working?
You can't manage what you can't see.
Right.
This is where we turn to the observability tools that are bundled in the mesh ecosystem.
And the main tool for visualizing the internal state of the mesh, the one that gives us that real-time graph of services and traffic, which one is that?
That would be Kiali. Kiali is the essential visualization tool. It takes all these abstract config objects, the virtual services, the destination rules, and it translates them into a dynamic graphical map.
So you can actually see what's happening.
You can see the health of services, trace a single request as it hops between microservices, and immediately spot bottlenecks or configuration errors.
It provides instant validation. If I deploy that complex match rule, I can just watch the Kiali graph and see if the traffic is flowing exactly as I intended.
That's it. It's the administrator's dashboard for troubleshooting.
Thank you for joining us for this deep dive into Service Mesh Essentials. We'll see you next time.